Machine learning, a brief overview. Machine learning is a subfield of artificial intelligence, AI, that focuses on developing systems that can learn from data and improve their performance on a specific task without being explicitly programmed. Essentially, it's about teaching computers to learn and make predictions or decisions based on data. How does it work? Data collection. Gathering relevant data is essential for training the machine learning model. Data preparation, cleaning, pre-processing, and transforming the data to ensure it's suitable for the model. Model selection, choosing an appropriate algorithm based on the nature of the problem and the data. Training, feeding the prepared data into the model to help it learn patterns and relationships. Evaluation, assessing the model's performance using various metrics to measure its accuracy and effectiveness. Deployment, integrating the trained model into a real-world application. Types of machine learning. Supervised learning, the model is trained on labeled data, where both the input and the desired output are provided. Examples: regression, predicting numerical values, and classification, categorizing data. Unsupervised learning, the model is trained on unlabeled data, and it must discover patterns and structures within the data itself. Examples: clustering, grouping similar data points, and dimensionality reduction, simplifying complex data. Reinforcement learning, the model learns through trial and error, receiving rewards or penalties based on its actions. Examples: game playing, robotics, and self-driving cars. Applications of machine learning. Machine learning is being used in a wide range of fields, including healthcare, diagnosing diseases, drug discovery, personalized medicine. Finance, fraud detection, algorithmic trading, risk assessment. Retail, customer segmentation, recommendation systems, demand forecasting. Manufacturing, predictive maintenance, quality control. Natural language processing, language translation, sentiment analysis, chatbots. Computer vision, image recognition, object detection, facial recognition. Machine learning is a subfield of artificial intelligence that involves training algorithms to learn patterns and make predictions or decisions based on data. Here are some key concepts and techniques in machine learning. Supervised learning. Training data is labeled. Algorithm learns to predict labels for new data. Examples: regression, classification, support vector machines. Unsupervised learning. Training data is unlabeled. Algorithm learns to identify patterns or structure. Examples: clustering, dimensionality reduction, principal component analysis. Reinforcement learning. Algorithm learns through trial and error. Receives rewards or penalties for actions. Examples: game playing, robotics, autonomous vehicles. Neural networks. Inspired by human brain structure. Composed of layers of interconnected nodes, neurons. Can learn complex patterns and relationships. Deep learning. Subfield of neural networks. Involves multiple layers of abstraction. Examples: image recognition, natural language processing, speech recognition. Model evaluation. Metrics, accuracy, precision, recall, F1 score, mean squared error. Cross-validation, training and testing on multiple subsets. Algorithms. Decision trees. Random forests. Gradient boosting. Support vector machines. K-means clustering. Python libraries. Scikit-learn. TensorFlow. Keras. PyTorch. This is just a brief overview of machine learning. If you have specific questions or want further information, feel free to ask. Mean, median, and mode. Mean, median, and mode are three types of averages used to describe the central tendency of a dataset. 1. Mean, also known as the arithmetic mean, calculated by summing all values and dividing by the number of values. Sensitive to outliers, very high or low values. 2. Median, middle value when the data is sorted in order. If there are an even number of values, the median is the average of the two middle values. Less sensitive to outliers than the mean. 3. Mode, most frequently occurring value in the dataset. Can have multiple modes if there are multiple values with the same highest frequency. Not affected by outliers. Example: dataset 1, 2, 3, 4, 5, 6. Mean 1 plus 2 plus 3 plus 4 plus 5 plus 6, /6 equals 3.5. Median 3, middle value. Mode, no mode, each value occurs only once. When to use each. Mean, continuous data, normal distributions. Median, ordinal data, skewed distributions, or outliers present. Mode, categorical data or discrete data with multiple peaks. Remember, these measures of central tendency provide different insights into the data. Choose the right one based on your dataset and research question. Standard deviation, SD, is a crucial concept in machine learning, representing the amount of variation or dispersion in a dataset. Here's a brief overview. Standard deviation, SD, measures the spread or dispersion of data from the mean value, calculated as the square root of the variance. Represents how much individual data points deviate from the mean. Why is standard deviation important in machine learning? 1. Data pre-processing, SD helps in scaling/normalizing data, which is essential for many algorithms. 2. Feature selection, SD can guide feature selection by identifying relevant features with high variance. 3. Anomaly detection, SD helps detect outliers and anomalies in data. 4. Model evaluation, SD is used in metrics like mean squared error, MSE, and root mean squared error, RMSE, to evaluate model performance. 5. Uncertainty estimation, SD can quantify uncertainty in predictions, essential for applications like risk analysis. Python libraries for calculating standard deviation. NumPy, numpy.std. Pandas, pandas.dataframe.std. Scikit-learn, sklearn.preprocessing.standardscaler. Remember, understanding standard deviation is vital for making informed decisions in machine learning and data analysis. Machine learning, percentiles. Percentiles are a statistical measure used in machine learning to understand the distribution of data. Here's a brief overview. Percentiles divide the data into 100 equal parts, each representing 1% of the data. Determine the value below which a certain percentage of data points fall. Used to understand data distribution, outliers, and data skewness. Common percentiles. 25th percentile, Q1 first quartile, 25% of data points are below this value. 50th percentile, Q2 second quartile, median value, 50% of data points are below this value. 75th percentile, Q3 third quartile, 75% of data points are below this value. Why are percentiles important in machine learning? 1. Data exploration, percentiles help understand data distribution and identify outliers. 2. Data pre-processing, percentiles can guide data normalization and feature scaling. 3. Model evaluation, percentiles can be used to evaluate model performance, especially for regression tasks. For anomaly detection, percentiles can help identify anomalies and unusual data patterns. Python libraries for calculating percentiles. NumPy, numpy.percentile. Pandas, pandas.dataframe.quantile. Scikit-learn, sklearn.preprocessing.quantile transformer. Remember, understanding percentiles is essential for making informed decisions in machine learning and data analysis. Machine learning, data distribution. Data distribution is a fundamental concept in machine learning, referring to the way data is spread out or dispersed. Understanding data distribution is crucial for 1. Data pre-processing, normalization, feature scaling, and handling outliers. 2. Model selection, choosing appropriate algorithms and hyperparameters. 3. Model evaluation, accurately assessing model performance. Common data distributions. 1. Normal distribution, Gaussian symmetric, bell-shaped curve. 2. Skewed distribution, asymmetric, tail on one side. 3. Bimodal distribution, 2 distinct peaks. 4. Uniform distribution, equal probability across a range. 5. Poisson distribution, models count data, often used for rare events. Tools for visualizing data distribution. 1. Histograms, bar charts showing frequency distributions. 2. Density plots, smooth curves representing density. 3. QQ plots, comparing distributions to a normal distribution. 4. Box plots, visualizing median, quartiles, and outliers. Python libraries for data distribution. 1. Matplotlib, matplotlib.pyplot.hist, matplotlib.pyplot.plot. 2. Seaborn, seaborn.distplot, seaborn.kdplot. 3. Scikit-learn, sklearn.preprocessing.normalizer, sklearn.preprocessing.standardscaler. By understanding and visualizing data distribution, you can make informed decisions in machine learning and improve model performance. Normal data distribution, also known as the Gaussian distribution, is a fundamental concept in machine learning. Here's a brief overview. Normal data distribution, Gaussian. Symmetric, bell-shaped curve. Mean, mu, median, and mode are equal. 68% of data falls within one standard deviation, sigma, of the mean. 95% of data falls within 2 sigma of the mean. 99.7% of data falls within 3 sigma of the mean. Characteristics. Continuous values. Infinite range, -infinity to infinity. Mean and standard deviation define the distribution. No outliers or skewness. Importance in machine learning. Many algorithms assume normality, example linear regression, principal component analysis. Used in data pre-processing, normalization, feature scaling. Helps in anomaly detection and outlier removal. Essential for statistical inference and hypothesis testing. Python libraries for normal data distribution. NumPy, numpy.random.normal. SciPy, scipy.stats.norm. Scikit-learn, sklearn.preprocessing.normalizer. Remember, understanding normal data distribution is crucial for making informed decisions in machine learning and data analysis. Machine learning, scatter plot. Scatter plots in machine learning. Scatter plots are a fundamental visualization tool in machine learning, used to explore the relationship between two numerical variables. They are particularly helpful for identifying trends, patterns, and correlations within the data. Key components of a scatter plot. X-axis, represents one variable. Y-axis represents the other variable. Data points, each point on the plot corresponds to a pair of values from the two variables. Interpreting scatter plots. Correlation. Positive correlation, as one variable increases, the other also increases, example height and weight. Negative correlation, as one variable increases, the other decreases, example hours of sleep and exam scores. No correlation, there's no clear relationship between the variables. Outliers, these are data points that significantly deviate from the general trend. They can influence the overall analysis and might need further investigation. Clusters, groups of data points that are closely grouped together. They might suggest distinct subgroups within the data. Example. Let's say we want to analyze the relationship between a person's height and weight. A scatter plot would show each person's height on the x-axis and their weight on the y-axis. If we see a general upward trend, it indicates a positive correlation between height and weight. Applications in machine learning. Feature engineering. Identifying relationships between features can help in creating new features or transforming existing ones. Model evaluation. Visualizing the relationship between predicted and actual values can help assess the model's performance. Exploratory data analysis. Understanding the distribution and relationships between variables can provide insights into the data. Anomaly detection. Identifying outliers can help detect unusual or unexpected patterns.